Welcome to another lesson on area, area of polygons in particular. This week we've been really diving into more of these formulas as well as where they come from. In particular, we've highlighted the area of the idea of annuluses or segments of circles, but really the notion of what we do with figures that have a larger area and a smaller boundary that's been removed from it. We talked about in the last lesson the area formula for that of a parallelogram or rectangle, as well as that of a triangle. And then we connected that with the idea of the area of a trapezoid, which is quite handy. And so what we need to talk about today as kind of our final components to address is how we would go about finding the area of polygons, in particular that of the kite and rhombus, as those are the polygons we haven't talked about that are special quadrilaterals. But more particularly, we're going to talk about the area of regular polygons. So can you find the area of a heptagon or a hexagon if I give you a little bit of information? Or even more generally, could you find the area of a 37gon based on some very basic information? So that's really where we're going today. Now, the good news is that the area of the kite and rhombus are very straightforward, just as we've been seeing with the area of trapezoids and parallelograms and triangles. And the reason for that is that the area of a kite and or of a rhombus, you can really think about both of these figures as being really a collection of triangles. And the reason for this being is that their diagonals are always perpendicular to one another. It's what gives it its characteristic kite or rhombus / diamond shape. And because of this, it means that if we actually draw in the diagonals of a figure, what you'll notice is that it breaks into 4 triangles. Well, what's interesting about triangles is that, as we know, triangles have half the area of the rectangle that would enclose the same length and width dimensions. So we notice that down here, this triangle is half of this box. We notice down here, this triangle is half of this box. Up here, this triangle is half of this box. And this triangle is half of this box, which means that all the triangles in aggregate are half the size of the box that surrounds them. Well, what are the dimensions of the box? Well, you'll notice that the dimensions of the box has a width which is as large as the first diagonal 1, which is the diagonal from non-vertex corner of your kite to non-vertex corner. And the height of the box is defined by the length of the diagonal from vertex corner to vertex corner, diagonal 2. Which means our area formula is half the product of those diagonals. Now you'll notice a rhombus, as a side note, a rhombus is also, keep in mind, a parallelogram. So we could also find the area of a rhombus in particular as base times height if that were easier for us. But we can also think of this idea of an enclosing box defined by the sizes of the diagonals. And again, we can use this just like any other formula in order to calculate unknown measurements. So if someone tells us the area of a kite in particular that we're interested in, and they tell us the length of one of the diagonals, and they want to know the length of the other diagonal, maybe for purposes of actually constructing some sort of kite with a certain surface area. And at this point, we simply go about distributing the half times the 30 to get 15. And then we divide both sides by 15. Getting us that diagonal 2 is going to be, I believe, 14? Man, it's late at night, but hopefully that's correct. So good news. We've been able to establish that the area of a kite or a rhombus is really defined also by the area of a rectangle and the fact that it is really subdivided into 4 triangles. Now, notice that people can get kind of cheeky in how they might ask these questions, and they might connect the ideas of area back to ideas of perimeter or other features that you know about these special quadrilaterals. In particular, you'll notice this question asker is really being a little bit tricky because they tell us the perimeter of a rhombus. And then they tell us what one of the diagonals is. Now you might say, how in the world is this helpful for us? And honestly, sometimes there's a little bit of skepticism that we might hold, and we might want to see where we go with this. Well, the reality is the perimeter, you'll notice, of a rhombus would not be useful if there wasn't a special property of rhombi, which is that all sides of a rhombus are the same length, right? A rhombus is equilateral. Again, that's what gives it its, oof, that was a horrible attempt, but that's what gives it its diamond shape, is that all of these sides are perfectly congruent. So what does that mean? Well, that means that each side is 17 units. Now, unfortunately, that doesn't quite tell us precisely what the exact measurements are going to be right now. And we might want to draw ourselves a picture in order to help us with this situation and to understand what's going on. So we have a rhombus, like so. Oof, that was not my best work. Let's try again. All right, they say third time's the charm. Let's see if that's the case. Great. Okay, so there's our rhombus, right? And we've established that one diagonal of this particular rhombus is 30 units. Okay. We know that each of the sides of this rhombus are 17. And we are asked to determine what the area of the rhombus is. Well, there's one thing we're going to have to remember, which connects back to where the area formula for a rhombus came, which is to say that a rhombus, if we recall, is a figure that has diagonals that are perpendicular to one another. And so if I draw in that diagonal right there, I know that it will be perpendicular to this orange diagonal. And not only is it perpendicular, but it also subdivides. And it subdivides perfectly by bisecting. In other words, it cuts this in half. This takes this from being 30 units to being 15 units here and 15 units here. Now, how in the world would we go about finding the length of the third diagonal? Well, you'll notice again, if we also keep in mind that each of these triangles are right triangles because, again, of the symmetry of a rhombus, and the fact that it's perpendicular, or its diagonals are perpendicular, then what we can do is we can then perform Pythagorean theorem in order to find the length of the third side. Now, what you'll find is that the length of the third side is 8, meaning that this whole diagonal that you see the pink written on is 16 units, which means finding our area is now just as simple as plugging in area is 1/2 the product of the diagonals. The 16 units, which is, let's say, the width of our box, and the 30 units, which represents the height of our box. We multiply all those things together, and we get 240 inches squared. Great. So again, keep in mind that while you may be fairly comfortable with the area formulas that we're introducing thus far, you really also want to try your best to be as fluent as possible working with all of the properties that you've been successful in learning and gathering, dealing with quadrilaterals in the past and the special types. It will help you significantly as you tackle these problems, and in particular, it helps most with these kite and rhombus problems. Okay, now again, to set up another problem, because again, it's somewhat useful to talk about this as well, but notice we could do things abstractly. Again, we're told the area of a rhombus is 168 centimeters squared, and we're told one diagonal is 3 times as long as the other. That means diagonal 1 is 3 times diagonal 2. So what does that mean? That means the area is 1/2 3 times diagonal 2 times diagonal 2. That's our area formula that we would work with. Of course, we actually have only one variable, which is diagonal 2. We would then get 2 diagonal 2 is 168, or we would learn that diagonal 2, in this particular instance, is going to be, try again, LabTad, mental math, 84 units in length, which is pretty handy. Cool. Okay, now we're really getting to the meat and potatoes, though, because the reality is, while it's nice to learn about a lot of these properties and these formulas, and it's nice to be able to relate things back to area formulas we already know, there does become a problem when we talk about larger order polygons. In other words, those with more sides. And again, we're talking about regular polygons such that all the sides are congruent and all the angles are congruent around the outside of that polygon. Now, what you'll notice as we go and we start investigating the areas of these polygons is something very curious that pops up. What you'll notice in particular is that if we take a polygon and we draw in what's called the radius, which again is the distance from the corner to the center of that polygon. Again, we've talked about a radius in terms of a circle, but again, we're talking about it here in terms of a polygon. We can actually draw in all these radii. And what you'll notice, if we do this, is we will find that we can subdivide every regular polygon into a bunch of triangular wedges, which is interesting. You'll also notice, if you're astute here, that really it's like finding the area of a circle and removing 5 congruent segments which connect all the way around the outside. So that's another way to think about the area of a pentagon in this case. Or we could remove 6 segments of the circle around the outside, thus creating a hexagon, and so on and so forth. But what we'll find if we start investigating this a little bit more closely is that to find the area of this pentagon, for example, we would need to find the area of this triangle. Now, I can't remember if we've introduced the terminology before, but there is also a measurement for the distance from the center of a side to the center of a circle. Or center of a polygon, which you'll notice is not the same as from the corner to the center. Because in a polygon, the distance from the corner to the center is further than the distance directly from the center of the side to the center of the polygon. Now, this distance here is what's called the apothem. It sounds like you're saying possum with a lisp. And so what we would need to do is know the length of whatever this apothem is. We would also have to know the length of each side, because the area of this triangle would be 1/2 apothem times the side length. That would be the area of this triangle. And then we would take this value and we would multiply this value by the number of triangles. In this case, we would multiply by 5 if we're talking about the blue. If we're talking about the purple, though, we would multiply by 6 because there's 6 sides and 6 triangles that we're subdividing into. If we're talking about the heptagon, of course, we would multiply that by 7, and so on and so forth. Now, one thing that gets a little bit cheeky that you'll notice about this area formula is a little bit tricky to spot, but it's something that mathematicians do in order to be a little bit kind of convenient. What they do is they look at this formula and they say, okay, so it looks like the area of every polygon is 1/2 the apothem times the length of the side times the number of sides, or number of triangles is a way to think about it as well. But what you'll notice is, those of you who are kind of familiar with this thinking, the length of a side times the number of sides. What is that? If I tell you that you have 5 sides in a regular polygon, that's not even an attempt. Let's pretend again. Okay, so here's our regular polygon with 5 sides, and I tell you that each side is 6 units. And I say, what is the 5 sides times the 6 units? Well, you get 30. Well, what is 30? It's the perimeter. In other words, when we look at this particular component right here, which says, what is the length of each side times the number of sides, this right here is really just perimeter. And the reason mathematicians like this is it allows them to condense the formula for the area of a regular polygon to be 1/2 apothem times perimeter, which is pretty cool. Again, you can see the other representation of this area formula is up here. You'll also see me sometimes reference this as the area of a triangular wedge times number of wedges. These are really the two ways to think about it. Subdivide the polygon into triangles and calculate the area of each triangular wedge and then multiply however many there are, or again, use this process of 1/2 apothem times perimeter. Great. So, how can we use this in practice? Well, again, we're going to look at some examples. So let's say someone has given us a regular octagon. Oh my goodness. Can LabTad draw an octagon? Nope. Oh man, well, is it just going to make it a circle every time? I'm going to cry deep tears. Okay, here we go. We're going to manually construct an octagon. It's going to look horrible. Ugh. Hopefully you all are having better luck than I am, because, you know, I mean, I get a cheat even, and I'm still not satisfied with my octagon. Oh, whatever. Good enough. All right, there's our octagon. And notice what we've discovered here is that we want to find the area of this octagon, given that we've been told that the radius of this octagon is 4 centimeters. Now, as we alluded to earlier, what we're really going to want to do is subdivide this octagon into 8 individual wedges. Once we've done so, we're going to need to find the area of one of these particular wedges. So let's take a blow up of that off to the side and see if we can work with it. So I'm going to take this section right here, come off to the side, and we're going to work with it over here. Here's our triangular section, our wedge. And what you'll notice is that each of these radiuses is 4 units. Now the problem that you might notice if we were to look at this situation is, you might say, well, Mr. Laptad, well, this is an isosceles triangle. We don't know that it's a right triangle. And in fact, we probably believe it to not be with certainty. So we can't do Pythagorean theorem to find the length of the third side, which is our side length of our actual octagon. We also can't do law of sines or law of cosines because we don't have any angles or anything to really work with. And that's almost entirely true. But there's one thing we have to keep in mind when we're working with regular polygons and regular polygon style problems. And it's that actually we do always know one of the angles in that particular triangle. Why? Well, because we know how many wedges we broke the triangle up into. And we know that all the wedges put together make a perfect 360 degrees. So if we ever want to calculate the angle at the top of a wedge, all that we need to do is take 360 degrees and divide by the number of wedges that we're subdividing into. So we take 360 and we divide by 8. This will tell me my central angle. Great. Well, what is 360 divided by 8? It's a number. Those of you who are faster than me at, 12:37 in the morning can probably calculate this, but it looks like it's going to be 40 and then 45, it seems, is what we're going to get for our central angle. So that means that angle at the top is 45 degrees. Now, again, we might look at a problem like this and go, okay, great. Well, now I could do law of cosines if I wanted to find the length of the third side. And you absolutely could, right? You could say, b squared is 4 squared plus 4 squared minus twice 4 times cosine of 45. Absolutely. That works just fine. But you'll notice there's something else you can do as well if you're not as familiar or comfortable with law of cosines. And what it is that you could do is you could draw in, for instance, an altitude for this triangle, which again, because this triangle is isosceles, would split it perfectly in half, meaning that you no longer would have 45 degrees here. In fact, you would have, you have completely erased everything that you did. No, you would have perfectly subdivided it into half of 45, which is 22.5 and 22.5. And that is the most illegible number I've ever written in my entire life. So let me try again. We're going to try with a smaller little pen here. So we're going to say if we break 45, it'll be into 22.5 and 22.5. Great. Okay, well, we've done a lot of work so far. What are we going to do next? Well, what we're going to say is, well, again, our goal, and again, when we actually did this, we turned this into some right triangles as well, because an altitude is always going to be perpendicular. Now we can go about finding the measurement of our base down here and of potentially our height. So how are we going to do that? Well, if we have things set up like this, again, we could have done law of cosines, and actually that would have technically been the fastest. But we can also just do basic trig. For example, I can set up here in this process, I can say, look, let's look at sine. Sine of 22.5 is going to be really, let's say, half of b over 2, or 0.5b, maybe is a little bit easier to represent. 0.5b, this is also 0.5b, because we split it in half. So this equals 0.5b over 4. Multiply both sides by 4 and divide by half. Same thing as multiplying by 2, so we could really multiply everything by 8 here. We'll get 8 times sine 22.5 is b. That's pretty cool. That tells me the length of each side. So maybe I should have used s for that instead of b, but c'est la vie, here we are. So that is the length. Oh my goodness, I'm going to lose my mind. Please let me draw a rectangle. Oh, thank goodness. It's terrible, but yeah, so now I've been able to find the length of each side of one of the wedges. The only thing I don't know is the apothem, but you'll notice by similar usage of trig, I can find this without any problems whatsoever. Because instead of doing, sine here, I could also do cosine, right? So I could say cosine of 22.5 is my apothem over, which is, again, apothem is the measure of height for one of these wedges. That's just the name for it. So the apothem divided by 4 in this case. Multiply by 4, and the apothem is going to be 4 times cosine 22.5. Now, why is this helpful? Because you'll notice the area of, again, one of these regular polygons is going to be the length of each side, which in this case is whatever 8 times sine of 22.5 is, times the apothem, which in this case is whatever 4 times cosine 22.5 is, divided by 2, because it's a triangle, so base times height divided by 2, multiplied by however many wedges we have, which in this case is 8, which means if we do get some approximations here, which I'll go ahead and pull up a calculator to help us with, we'll be able to give an approximation for the area of the entire regular octagon. And as long as we're saving our values as we go for the length of B and A, for example, we'll have a fairly accurate measurement. So I'll go ahead and pull up my calculator, and then we'll be good to go. So again, our area formula that we're using, just to reference it for this particular problem, is this one here, which is we're finding the area of one of those triangular wedges times the number of wedges. Okay, so how do we find the area of one of those triangular wedges? Well, again, the area of the wedge is 1/2. Our base, which is that, comes from that 8 sine 22.5. Okay, so 8 times sine 22.5. So I get that that's about 3.06. And then we're going to do that times the height, which is the apothem in this case, which is 4 times cosine of 22.5, which is about 3.70. So I will multiply those two together. Divide by 2 for 1/2. So the area of each wedge is about 5.66 units squared. I keep in mind that I don't just have one wedge, but I actually have 8 wedges. So I'm going to multiply this by 8 in order to fully calculate the area of my octagon. Meaning that the area of my octagon is around area of, here's LabTad's attempt to just draw a terrible octagon. Area of an octagon is about 45.25 units squared. Great. So what you'll notice as you look at these styles of problems is that they're often much more involved, because a regular polygon is going to be a little bit more complex depending on the number of sides that it has. But the process is all exactly the same. What you're going to do is you're going to simply draw an image or something to kind of help you get an idea. But you'll notice that that particular regular polygon gets divided into as many wedges as there are sides. And you can use that information about breaking it into wedges to find what the central angle has to be at the top of each of those particular wedges, dividing 360 degrees by the number of wedges that you're subdividing this particular polygon into. You can then either do law of cosines, or you can go ahead and draw in some sort of height and do basic trig in order to find the height of the apothem, which is from bottom to top of a wedge, as well as the length of the base, which is the side length of the wedge. Okay. Deep sigh. That was a lot, right? And what you'll find is that it is fairly involved. Now, this can build. And again, you'll see in this next example, like right here, this process is almost the same as the previous one. So we have a regular octagon, we have 15-inch sides, we have a radius of about 19.6. This one's actually a little bit faster. The reason being is that we have everything that we need for our formula, because the area is 1/2. Oh, we don't have everything, but we have a lot. The apothem times the perimeter. And again, if we're looking at a situation like this, we notice that we have an octagon that just so happens to have 15-inch sides. It has a radius of about 19.6. The only thing we don't know is the apothem here. That's not an issue though, because again, if we wanted to, we could calculate that. And in fact, let's do it. Again, An easy way to do this here would be Pythagorean theorem. This is going to be 7.5 on each side, so I'll do 19.6 times 19.6 minus, in this case, 7.5 times 7.5, and we will square root that. This gives us about 18.11 is about the length of this apothem right here. So the apothem is about 18.111. And again, we did that by doing Pythagorean theorem in this case, since we actually knew both the radius and the side length, which is great. So now we could go over to our formula if we wanted to and say, hey, I'm going to plug in about 18.11. What's my perimeter? Well, it's 15 times the 8 sides that I have, 120 units, and I need half that. So I go ahead and throw that in a calculator, and I find that the area is approximately 1,086.50 inches squared. Again, the formula is handy, and in this case, we had more information about the dimensions of the wedge. We knew the whole side length in this case and the radius. So all these things were handy for us as we moved forward. Now we're going to skip C for a second in order to look at D, which is really the ultimate wombo combo. And I know we've been going for a while here. I really appreciate your patience. But this is the ultimate place that area calculations can build. And the reason that it's so difficult is because you'll notice what we have here in this particular situation is we had some larger hexagon that then we removed a smaller hexagon and a trapezoid from. So really, if we want to know the area of this shaded region, we need to know the area of the big hexagon. Then we're going to take away from that the area of the small hex. And we're also going to subtract off the area of the trapezoid. This gives us the area of the shaded. Wowza. Well, where are we going to go with this? Well, again, this is going to be fairly involved, but again, I believe in our ability to be successful here. You'll notice if we take one of these wedges, for example, in this smaller figure here, and we go and we blow it up, this might be handy, or maybe we'll do the larger one here. We know the radius that R is 20 for each of these, which means this distance here is 2R or 40 units. So we're going to look at that wedge right there of our big figure. We're going to find that this is 40 units. We also know that a hexagon has 6 major wedges that we are subdividing it into, which means, as I try to draw the rest of this triangle here, that if we take 360 and we divide by 6, it means that at the top of each of these wedges, we have exactly 60 degrees. Drawing in the height, as we've done, splits it into 30 degrees, which means, we have a 30, 60, 90 triangle. Now, the advantage of this is, of course, we don't have to do Pythagorean theorem, we don't have to do trig, we don't have to do anything complicated. All we have to do now is remember 30, 60, 90 rules, which is to say, to go from the hypotenuse to the short leg, we need to divide, and the factor of change is a factor of 2, which means that if the hypotenuse is 40 units, it means that the short leg here is 20 units, and it means the hypotenuse is 20 root 3 units. So again, if we remember, well, again, this is also 20, which means each side length is 40. So if we're talking about finding the area of this hexagon, what we would need to do is, this big hexagon, is we would need to find the area of one of the big wedges of which this is. So this would be 1/2 our base of 40 times our height of 20 root 3. That's the area of one of our wedges times the fact that we have 6 large wedges, 1, 2, 3, 4, 5, and 6 in that figure as a whole. So we multiplied the whole thing by 6. Oof, we go ahead and simplify things. We're going to get, in this case, 2400 root 3 is the area of our big hexagon. And now we can repeat the same idea, the same process for our small hexagon, and then ultimately our trapezoid. Our small hexagon, again, is actually going to have the exact same situation. It's also a hexagon, which means it's also going to have 30 degrees at the top in each of these once we've split that 60 in half. This is 20 units in this particular case. This is then 10. This is then 10 root 3. Great. That's very, very handy to see. So that means the area of the small hexagon is, again, 1/2. Our base, in this case of 20. Our height, in this case of 10 root 3. And multiplying by the fact that we have 6 of these particular small wedges. 1, 2, 3, 4, 5, and 6. So we've gone ahead and multiplied that by 6. We're going to get, in this case, 600 root 3. The last thing we need to find is we need to find the area of our trapezoid. Now, it just so happens that if we look carefully, we will notice a couple things. One, we'll notice that the top of the trapezoid is really just one of the sides of my small hexagon, which we know that the sides of those are 20 units. We know that the distance along the back side is really the length of one of the large sides of my hexagon, which in this case is 40 units. And we actually know the height of this is also the height of A, the apothem in either of these cases, which is 10 root 3. 20 root 3 if we're looking at 2A, but 10 root 3 if we're looking at 1. That means that the area of the trapezoid is really easy. It's the average base. Well, the average of 40 and 20 is 30, times 10 root 3. And this right here, folks, is the area of our shaded figure. Notice that actually all of these terms are counting in regards to root 3s, so I have 2,400 minus 600 of them minus 300 more of them. I've taken away 900 of these, leaving me with 1,500 root 3 is the area of my shaded figure. Wow. Again, a very, very complex, very involved process and problem, something that requires a lot of layers and in fact involves 3 area calculations as well as combining with the notions of finding the area of larger objects when sections of them have been removed. Again, this is as complex as area could ever get, and you'll notice its complexity is really tracked by the fact that you're doing multiple problems in one process. But as long as you keep this idea in mind of writing yourself out some general battle plan, so to speak, at the beginning, as to how you're going to find the area of what you're investigating, and then you go section by section to find the area of each of these pieces, keeping in mind this idea of breaking your polygons into wedges to find their areas, you're going to find that things end up moving in the exact same pattern and in the same clip, which is really, really handy and reliable. All that to say, thanks so much for your time today and for tuning in for this. I hope this was helpful, even if it was quite involved. Thanks so much.